Okay, welcome everyone to our final plenary session, 11B. So this session we will have again 6 talks on intervening magneto-ionic material, um, which will be probed by the polarization of FRBs. So I guess we should get started. So our first speaker will be a recorded talk from Alvina Yee Lian On from University College London, National Tsinghua University in Taiwan. Her topic would be probing the magnetic universe with FRBs. Go ahead, Alvina.
Magnetic universe with fast radio bursts. Take it away.
All right, thank you, Jason. So first of all, thank you to the organizers for giving me this opportunity to talk today. And I'm Alvina, and I recently obtained my PhD degree from UCL, and I will be starting a postdoctoral position in Taiwan in a few months' time. So as you can probably see in my background, I'm currently in very, very sunny Brunei. So it's a really tiny country in Southeast Asia, and I'm working from home like many of you. So in the last 2 weeks, we heard several talks about how magnetic fields are important in the context of FRBs, possibly playing an important role in the physical mechanisms and the emission mechanisms. So today I will share a little bit about how we can probe the magnetic universe with FRBs acting as cosmological lighthouses. So we know that magnetic fields are everywhere around us, but the elephant in the room is, where did the first magnetic fields come from? And how do they evolve with the structure formation of the universe? And the reason why it's challenging to study magnetic fields is because it's simply invisible to the eye, and we can only infer their existence and properties through indirect methods. And here in the background of my slide is the beautiful Northern Lights, which is a wonderful evidence of the Earth's magnetic field interacting with solar wind. So if we move on to larger scales than the sun and the Earth, the galaxy that we live in is also magnetized, as well as larger scale structures such as nearby galaxies and galaxy groups. However, when we move to bigger scales, like for galaxy clusters and beyond, it becomes more difficult to see and measure the magnetic fields because they're simply a lot weaker. However, it is important to correctly infer the magnetic field properties at such large scales because they may hold some evidence of the first magnetic fields. Now, the question is, we still don't know whether the first magnetic fields is primordial in origin, meaning they're generated soon after the Big Bang, or maybe they're generated through some astrophysical processes after the first stars and the first galaxies form. So some numerical simulations like the one I'm showing on the left here, and radio observations of nearby superclusters and cosmic filaments roughly constrain the seed magnetic field strength to be roughly the order of nanogauss. So most of you have probably seen this equation before, and we know that the magnetic field is usually measured using the rotation measure at radio wavelengths. So by definition, the rotation measure quantifies the amount of rotation that occurs when the polarization plane of light rotates in a magnetic field. So observationally, we obtain the rotation measure by measuring the change in the polarization angles on the sky at various wavelengths. For example, the coma cluster here. So on the left, we can tell that the intracluster medium is magnetized through the detection of diffuse megaparsec scale radio contours here in green. And if we use bright polarized radio sources behind the cluster, we can fit polarization angles against wavelength squared to obtain the slopes of best fit, which actually gives us the rotation measure, and hence some indication of the magnetic field strength along the line of sight. So apart from radio sources and quasars, FRBs can also be used as cosmological lighthouses to diagnose large-scale magnetic fields in a similar way. So in fact, I would say that FRBs have an extra advantage of breaking the degeneracy between electron density and magnetic field because of their unique observable, which is the dispersion measure. So if you consider both the DM and RM, many previous works have constrained the large-scale magnetic field strength to be of the order of below tenths of nanogauss. And here, if you're interested to find out more what we can do with FRBs as cosmological probes, feel free to check out my collaborator Tetsuya's talk, which I believe is now on YouTube. So what's truly exciting here is that soon enough, we should be able to put more stringent constraints on the first magnetic fields when the world's largest radio telescope, the SKA, comes online. And the SKA is expected to carry out an all-sky survey of millions of extragalactic rotation measures, which is many, many times of what we can see now. And for comparison, on the left is our Faraday sky in 2012 with about 40,000 sources, whereas on the right is the latest Faraday sky map, which came out early this year with over 55,000 sources. And what we can see here is that the large-scale features of the field remains largely unchanged between the two maps, but the small-scale information related to the magnetic field of the Milky Way has greatly improved with a higher density of rotation measures. So we can imagine that with more extragalactic background lighthouses being detected and being localized, such as FRBs, the SKA would have a huge impact on cosmic magnetism science. So it is timely and very important for us to gain a better understanding of the rotation measure method and how it is related to the magnetic field strength along the line of sight. So this equation is widely used and it is derived from the theory of polarized radiative transfer, assuming that there's no absorption, no emission, no Faraday conversion, and that only thermal electrons are present. And it is often argued that the correlations in the observed rotation measure fluctuations tell us about the length scales on which the magnetic fields vary. Now, the conventional approach is to model the rotation measure fluctuations as some kind of random walk process. So as such, the standard deviation of the rotation measure actually quantifies the fluctuations in the line of sight magnetic field. And most studies on cosmic magnetism actually use this expression I'm showing here.
Hi.
So the big question is the equation really valid in all astrophysical scenarios? When is it justified to be used? And when does it deserve caution? So to address this question, I carried out Monte Carlo simulations to compute the rotation measure fluctuations. First using the conventional approach I showed earlier, and then I compare it with the results from a standard polarized radiative transfer calculation. And here is one of the key results from the conventional approach. So let's do an eye test remotely, everyone, and see if you can spot any difference between each panel that I'm showing here. Do you see any difference at all? Well, the answer is no. They all pretty much look the same. And there's nothing wrong with our eyes. But what if I tell you that these are actually rotation measure maps that are generated using completely different distributions of density and magnetic fields? So in fact, what you're seeing here in the top panel are generated from densities and magnetic field strengths, which have a Gaussian distribution, whereas the ones in the bottom have uniform distribution for the densities and magnetic field strengths. And furthermore, for the ones in the bottom, I deliberately made the magnetic fields unphysical and non-divergence free. So what this shows us is that from just by looking at the rotation measure maps alone, it is not a trivial task to characterize the electron number densities and the magnetic field strengths. Now, not only that, we also found that the conventional approach is unable to distinguish between various distinct distributions of densities and magnetic field strengths. So what I'm showing here in the red dotted box is that the conventional approach cannot actually tell apart whether the distributions of densities are uniform, Gaussian, fractal, or log normal. And it's the same case for magnetic fields as well. Apart from that, the conventional method also do not work for distributions with fractal and log normal density distributions. Now, this is actually quite a problem because fractal and log normal density distributions are actually quite common in many astrophysical systems, such as the ICM and molecular clouds. And in the last couple of minutes that I have, I wish to highlight several subtleties that we should be aware of if we want to quantify rotation measure fluctuations correctly. So first of all, the fluctuations of density and magnetic field strengths along the line of sight and across the sky plane can be different. So I'm showing here is an illustration. So what we see here on the sky are two similar angles. However, each one of them has a different characteristic length scale along each line of sight A, which has two length scales, and B, which only has one. Now, what's interesting is that each of these length scale do not actually correspond to the length scale that we see on the sky. So what this means is that when we take a radio picture of the sky and derive a correlation length scale of the magnetic field, this does not necessarily translate directly to the correlation length scale of the magnetic fields as they evolve from the past to the present. And another point to take note of is the possible contamination in the power spectrum that we measure. So in reality, the power spectrum of the observed polarization may be contaminated by emissions from the intervening medium and the embedded sources along the line of sight. So for example, we carry out a radio observation of the sky at a fixed frequency. So observationally, the power spectrum we measure is the result of the contributions from sources at different redshifts. And we pick up different components at higher wave number K. On the other hand, theoretically, a snapshot of a cosmological simulation only allows us to pick up all the sources at a single redshift. So it does not contain any contribution from the higher redshifts. And hence, when we see, for example, a higher power in the smaller scales in our power spectrum, for example, it may not be truly from the magnetic field itself. It could be due to, for example, emissions from the medium and embedded sources at different redshifts.
About 2 minutes, Alvina.
Oh, thank you. Right, so in the last 2 minutes, in summary, the key take-home message from here is that to please be very careful when we try to interpret magnetic field properties from rotation measures. And I would strongly suggest a polarized radiative transfer calculation as a more robust alternative. So if you're interested in more details, please take a look at these two papers here, or feel free to ask me any questions after this or in Slack if you're catching up on YouTube. So that's all from me today. Thank you very much.
Are there questions to the speaker? I don't think the speaker will be here to answer questions. If you do have questions, you can post on the Slack channel. So let's go to our next talk. Our next talk would be from Stella Ocker, which will be a live talk. She's from Cornell University. She will be talking about leveraging the combined scattering and DM budget. Take away.
Okay, thank you. Are you seeing my screen okay?
Yes.
Okay, thanks. All right, hi everyone. I'm Stella and I am a fourth year PhD student at Cornell working with Jim Cordes and Shami Chatterjee. And today I will be talking about leveraging the combined DM and scattering budgets. So FRBs are generally extragalactic and propagate through a wide range of ionized media along their journey to the observer. And today I'll be focusing on how a joint assessment of both the DM and scattering budgets can be used for a wide range of utilities to probe both this ionized gas and for other utilities as well. So first I'll talk about how we can use scattering to probe turbulent density fluctuations in ionized gas along the line of sight. These density fluctuations generally follow a power law wave number spectrum, where Cn squared refers to the amplitude of the wave number spectrum and beta equals 11/3 for Kolmogorov turbulence, and the spectrum extends from an outer scale Q0 to an inner scale Qi. Now, I'll also be talking about how scattering can actually be used to assess the plausibility of host galaxy associations, and I'll briefly talk about new work on how scattering can improve estimates of DM contributions from host galaxies and the corresponding redshift estimators. So there are three main scattering observables: pulse broadening, scintillation bandwidth, and angular broadening. This diagram in the middle shows a ray tracing simulation where these black lines are arbitrary rays launched from a source at S through a homogeneous medium to an observer at O. And all of these colored lines show the rays that actually reach the observer. So you can see that the rays with the largest angles of arrival also correspond to the longest ray paths and the longest time delays. This diagram on the left is showing the kind of two-screen scattering geometry that we believe may be relevant for many FRBs. Now, the amount of pulse broadening that's given per unit DM can be simply quantified using the fluctuation parameter. So the relationship between tau, pulse broadening, and DM is given by this relationship here, where nu is the observing frequency, G scat is the geometric leverage factor, which I'll talk about in a few moments, and F tilde refers to the fluctuation parameter. So this fluctuation parameter arises in the ionized cloudlet model from the statistics of density fluctuations in the ionized gas. So zeta and epsilon squared refer to variations in the mean density and the density fluctuation variance. And then we also have the filling factor F and the spatial outer and inner scales of the turbulence wave number spectrum, LO and LI. And so you can see that the fluctuation parameter very compactly describes the unknown quantities probing density fluctuations in the gas, and that it gives us a direct relationship between two observables, pulse broadening time and DM. Now, the pulse broadening time is also directly related to the other scattering observables. It's inversely related to the scintillation bandwidth, and scintillation bandwidth and angular broadening are related to each other by the distance to the scattering screen for a single screen scattering geometry. And when we talk about scattering in an extragalactic screen or lens, we also need to apply a redshift correction to account for time dilation. So you can see from this simple relationship between scattering time and DM that constructing a scattering budget inherently involves the DM budget, the fluctuation parameter, which varies between different line of sight components, and finally, the geometric configuration of the source, lens, and observer given by G-scat. So G-scat is given by this equation down here. It's related to the relative distances between the source, lens, and observer, and it's also related to the path length through the lens, L. So this plot on the right gives the geometric factor versus the ratio of the lens to source redshifts, and these different curves are for different values of the source redshift. So you can see that generally speaking, the scattering will be amplified the most by geometric configurations where the lens is about halfway between the source and observer, but the amount of amplification will change depending on how large the source redshift is, and also it will change depending on the F tilde fluctuation parameter and DM contributions of the lens. So I think it's easiest to develop a physical intuition for the fluctuation parameter by calibrating it to the Milky Way disk. So this plot is showing you the distribution of pulse broadening time divided by DM squared for all galactic pulsar scattering measurements. And on the right-hand axis, you can see the equivalent value of the fluctuation parameter versus galactic latitude. And so this blue band is showing the mean value of the fluctuation parameter for galactic latitudes above about 20 degrees, which corresponds to lines of sight dominated by the diffuse thick disk. These are also lines of sight relevant for many FRBs. So the mean value of the fluctuation parameter in this region is about 0.003 with these kind of funny units because of the fluctuation parameter's dependence on the outer and inner scales of the turbulent spectrum. But you'll also notice that as you move towards low galactic latitudes, so into the plane of the galaxy, and also looking towards the inner galaxy, which is highlighted by these orange crosses, you see this orders of magnitude increase in the fluctuation parameter, and this directly corresponds to the physical structure of the ISM in these different regions of the galaxy. So as you move into the plane, you start sampling the spiral arms, significantly more H2 regions, star-forming regions, supernova remnants. The ISM is much more inhomogeneous, and you see enhanced scattering. And so the value of the fluctuation parameter is much larger in the galactic plane and towards the inner galaxy than in the thick disk. So this variation in the fluctuation parameter between different regions of the galaxy is actually one of the reasons why the galactic pulsar tau-dm relation does not directly apply to extragalactic sources like FRBs. And so if you're interested in hearing more about how the fluctuation parameter is related to this tau-dm hockey stick relation and what that means for using the tau-dm relation for extragalactic sources, you can feel free to ask me later. So we can use this simple formalism relating scattering time and dm and the fluctuation parameter to actually constrain the amount of scattering that comes from galaxy halos and to constrain the corresponding fluctuation parameters. And so we do this first for the Milky Way halo. And to give away the punchline early, our analysis indicates that scattering from galaxy halos is negligible for the lines of sight that we analyze. So we approximate the amount of scattering coming from the Milky Way halo as being less than or equal to the total amount of scattering that's observed. In this case, we use two FRBs, 121102 and 180916. These two FRBs are repeaters, they're localized to their host galaxies, and in the literature, there are very precise characterizations of their scattering measurements. Now we take that total scattering and we subtract the amount of scattering that's expected from the Milky Way disk. This is constrained using NE2001, which is based on the empirical distribution of galactic pulsar DMs and scattering times. And we ultimately put this through a likelihood analysis of the FRB scattering to obtain an upper limit on the product of the fluctuation parameter and dm squared for the Milky Way halo. And so then we can apply a given dm model for the halo to obtain an upper limit on the fluctuation parameter. Now we actually do a very similar analysis for two other FRBs that have galaxy halos intervening their lines of sight, and those are FRBs 181112 and 191108. So before I go ahead and show you our final constraints on the fluctuation parameters for these various halos, I'll briefly demonstrate an example of the scattering budget for FRB 121102. So because 121102 has both an angular broadening and a scintillation bandwidth, we can actually constrain the distance to the dominant scattering screen along this line of sight. So this plot on the left shows the measured angular broadening in blue, and then the angular broadening predicted by the scintillation bandwidth in green. So the overlap of these two curves gives the distance to the dominant scattering screen, which we find is about 2 kiloparsecs, consistent with the distance to the outer spiral arm. So this plot on the right is showing the dm, density, and CN squared predicted by NE2001 along this line of sight, and we find very good correspondence between NE2001 scattering predictions and the observed scattering measurements for this line of sight. This all implies that the amount of scattering from the galactic halo along this line of sight is negligible because we see strong evidence that the scattering is dominated by the outer spiral arm. So now I'll jump ahead and show you our final limits on the values of the fluctuation parameters for the various halos we consider, and also some different values for the galactic ISM. So here we have M33, which has the foreground halo of FRB 191108. We have the foreground halo for FRB 181112, and then the galactic halo, as I said, we constrain using 121102 and 180916. We also have a value of the fluctuation parameter for the Large Magellanic Cloud. This comes from the scattering time of pulsar BO540-69. This pulsar lies inside a supernova remnant, giving rise to a very large fluctuation parameter, actually comparable to values of the fluctuation parameter typical for the inner galaxy in the Milky Way. Now, you'll also notice that the values of the fluctuation parameter for these three halos are quite small, and the equivalent amount of scattering expected from these halos is also small to negligible. So the amount of scattering from these different regions is given on the right-hand side. Now, we can also actually use the fluctuation parameter as a potential diagnostic for multi-phase models of the circumgalactic medium. So in particular, in the warm ionized medium, we expect that the fluctuation parameter will be much larger than in the hot ionized medium because the filling factor in outer and inner scales are much smaller than in the hot ionized medium. And our initial analysis suggests that galaxy halos contribute negligibly to the scattering of the well-characterized lines of sight that we consider, which may favor that hot ionized medium, but further analysis may potentially be able to distinguish between models where the CGM includes cooler, clumpier gas. So I'm now going to switch gears and talk about another application of scattering times, which is actually assessing the plausibility of host galaxy associations, and in particular using the example of FRB2021. So you heard about the polarization of this source in Reshma's talk, and Dee Lee will be giving a much more detailed description of this FRB's discovery in the late-breaking news session later this evening. But the brief story is that this FRB was localized to a dwarf galaxy at a redshift of 0.24, and the implied host galaxy DM contribution for this FRB is extremely large, about 1100 parsecs per cubic centimeter in the host frame. And so one of the alternative explanations that we explored for this line of sight was, what if the observed galaxy association is actually a foreground galaxy intervening our line of sight to a background FRB source? And what we determined is that the observed scattering time is actually much too small to allow this scenario to be plausible. So this generally comes down to the behavior of this GSCAT leverage parameter. It's about 1 for scattering in the host galaxy, but GSCAT will be orders of magnitude larger for scattering in an intervening galaxy. So this plot on the right is showing GSCAT versus the host redshift for a fixed lens redshift of 0.24, and these three curves are for different values of the path length through the lens. So you can see that as we place the host galaxy behind our observed galaxy, we would expect GSCAT to get orders of magnitude larger, and the implied amount of scattering is on the order of seconds. And so our observed scattering time, which is about 10 milliseconds at 1.3 gigahertz, is actually far too small to allow this observed galaxy to be an intervening galaxy. So this leaves us with the intriguing puzzle of how this little dwarf galaxy contributes this extraordinarily large host DM. Now I'm going to finish up by briefly advertising some new work led by Jim Cordes, which just recently hit the archive. And this work is on how scattering can actually be used to improve estimates of host DM contributions and the corresponding host redshift estimators. So the basic idea is that from a constraint on the host galaxy scattering contribution, you can actually constrain the host DM contribution for plausible ranges of the fluctuation parameter. And then you can plug in this estimate of DM host into the DM budget in the normal way to get a redshift estimate. So we have essentially constructed a Bayesian analysis that connects the FRB DM and scattering budgets with redshifts to constrain the host DM contributions for all currently localized FRBs. This plot on the right is showing an example for FRB2021-23. In this top panel, we have the estimated DM host contribution, and then in the bottom panel, the scattering time contribution. And this is versus the host galaxy redshift. So this red line corresponds to the measured redshift, and then this green horizontal line corresponds to the measured scattering time. And so you can see that if you make the host galaxy redshift too large, then you essentially reduce the amount of scattering that is allowed from the host galaxy. And so the amount of scattering that you observe actually sets a limit on what the host galaxy redshift can be. So for localized FRBs, this kind of analysis can be used to test host galaxy associations. And we've actually found that for unlocalized FRBs, incorporating scattering into the DM budget can actually improve redshift estimates. So for more on that, I highly encourage you to check out this archive paper. And I'll also briefly note that this scattering-based...
You have 3 minutes.
Okay, thank you. I'll also briefly note that this scattering-based redshift estimator is actually sensitive to FIGM, the cosmic baryon fraction. And the main reason for this is that if you make FIGM too large, then the DM from the IGM will dominate the DM budget, and you essentially don't have enough DM from the host allowed to account for whatever your observed scattering is. But if you make FIGM too small, then the DM budget will be dominated by the host DM contribution, and the implied amount of scattering will be far too large to explain whatever you observe. So this plot on the right is showing the RMS residuals between the estimated and observed redshifts of 9 localized FRBs. And this top blue curve is showing the residuals for the DM-only redshift estimator. And then these bottom two red and green curves show the DM and scattering-based redshift estimators, and these are versus FIGM. And so you can see that the residuals for the scattering-based redshift estimator actually turn up after a value of about 0.9 for FIGM, indicating that our RMS residuals are broadly consistent with the range of FIGM that's been implied by previous studies. So I will now briefly wrap up this talk. So I've talked about this simple formalism relating pulse broadening time and DM through the fluctuation parameter, which is a very concise and simple way of probing the characteristics of density fluctuations in ionized gas along the lines of sight to FRBs. We apply this formalism to analysis of FRB scattering in halos, and we find that halos contribute negligibly to the scattering of the FRBs that we consider. And I've also talked about how scattering times can help inform host galaxy associations and improve redshift estimates. So with that, I will wrap up and take any questions.
Thanks for the talk. So we already have a question from Zorara. He was asking, how does the Kolmogorov spectrum and fluctuations assumed here compare to that tuned in cosmic ray propagation codes for cosmic ray diffusion to match observations like Gal probe or Dragon 2? I actually don't know how these simulations are done.
That is a good question, and I am also not very familiar with the cosmic ray diffusion codes. So I will have to look into that to be able to answer. Sorry.
So Vikram has a question. Could you comment on the expected level of sightline to sightline variance in the host scattering, maybe based on the Milky Way?
Yeah, sure. So we would probably expect to see a much larger scattering coming from close to the centers of host galaxies versus the edges. And the amount of scattering that we see will also vary depending on the inclination with which the line of sight is piercing that host galaxy. And so you can imagine that if you're seeing a host galaxy edge on, then depending on where the FRB source is within the host galaxy, you might end up seeing much larger scattering than if you're piercing the host galaxy from, say, face on, so only piercing through, say, the top half of the disk. Yeah, so hopefully that kind of answers that question.
Yeah, another question is, you mentioned there's a relationship between tau host and DM host. So how reliable is that if the FRBs are still embedded in supernova remnants? You know, are the Milky Way ISM calibrated relations still reliable?
Yeah, so if you're talking about using, say, the tau DM relation that's constrained for galactic pulsars, is that what you mean, or do you mean just using an agnostic? Okay, yeah. So if you're trying to use the relationship between tau and DM that's constrained from galactic pulsars, then it's going to be a little bit complicated, because it might be okay to, say, use the high DM portion of this diagram. Sorry, I'm going to try to go back to this plot so that my explanation will make more sense. So if you have a source, say, embedded in a supernova remnant, then that may mean that this kind of high, steeper portion of this tau DM relation might be applicable, because this corresponds to lines of sight that are closer to the galactic plane in the inner galaxy, where you would have more pulsar sight lines that, say, intersect supernova remnants or H2 regions. So in that sense, it might be okay, possibly, but yeah, that's the answer. And generally, the fluctuation parameter will be larger if you have the FRB source still embedded in the supernova remnant.
I see that Jim had a comment saying that the range of F tilt they consider is large enough and probably encompasses the galactic variance.
Yeah, that's also true.
Yeah. Are there any other questions? Oh, there is one from on the Slack channel. So in DM host, this is from Javier Prochaska. In DM host, do you distinguish between host ISM and halo gas? Like you did for the Milky Way?
Yes, yeah. So we typically distinguish between the ISM, which we often refer to as the disk, although that gets a little more complicated if you're talking about different kinds of galaxies versus the more diffuse halo gas. Yeah.
Thanks. So we don't have any other questions. I guess we should move on to our next. Oh, Vikram is asking, but let's move on. I will copy and paste that one to Slack channel so that you can reply. So we will move on to our next speaker, which will be a recorded talk. So this one is from Ryuichi Takahashi from Hirosaki University. He will be talking about statistical modeling of the cosmological DM.
Thank you for giving me a chance of the talk. My name is Ryuichi Takahashi, and I'm working on this project in collaboration with Ocker-san. And this talk is based on a paper published in NRAS. So if you are interested in my talk, please check this paper later. And in this talk, DM stands for the cosmological dispersion measure, including ionized gas, comes from ionized gas in IGM and intervening galaxies. And in this talk, we don't consider the Milky Way contribution or host galaxy contribution. And previously, there are two theoretical approaches for the DM statistics: analytical approach and numerical simulation approach. And the analytical approach commonly uses based on the halo model. And the other approach is numerical simulation approach. It uses cosmological hydrodynamic simulations. And our approach is, how can I say, hybrid of these approaches. So we made analytical model calibrated with the latest cosmological simulations. And the main purpose of our study is, the first purpose is we model the 2-point statistics of dispersion measure using the hydrodynamic simulations, latest hydrodynamic simulations, Illustris TNG 300. We first measure the free electron abundance and power spectrum of its spatial fluctuations, because you know, the DM statistics are fully determined by the free electron statistics. The DM statistics are just a projection of the free electron statistics. And we then provide analytical model of the DM statistics using fitting functions of the free electron distribution. And next, we then validate our analytical model against mock DM measurements. And let me briefly mention Illustris TNG 300. In the previous session, Fei Wong already mentioned, I think, this simulation. This is the state-of-the-art hydrodynamic simulations, and the simulations follow gravitational evolution and astrophysical processes. including star formation, gas cooling, and stellar and AGN feedback. And the simulations reproduce free electron distribution in the universe. And there are 3 different resolutions named TNG 301 to 303. And 301 has the highest resolution. And that and TNG team also released a dark matter only simulation named TNG 301 dark. And this dark matter only simulation can be used for studying the difference between the free electron distribution and dark matter distribution in the universe. And this is the result. This figure plots the free electron fraction measured from the TNG simulations. The vertical axis is free electron fraction as a function of redshift. And free electron fraction is defined as number of free electrons over total number of electrons. So total number means, let's say, free electrons and electrons bound in atoms. And the colored symbols are the results measured from TNG simulations. And according to the simulations, the current free electron fraction is about 95%. And the red curve is our fitting curve. And this figure shows the power spectrum of the cosmological free electron distribution. And this is, how can I say, one of our main results. And the vertical axis is power spectrum as a function of wave number k. And the colored symbols are the result measured from the simulations. And the gray open symbols are dark matter power spectrum measured from dark matter only simulation. And the bottom panel plots the bias factor. Here, bias is defined as the free electron power spectrum divided by the dark matter power spectrum. And the red curve is our fitting curve. And you can see at large scales, free electrons exactly trace the underlying dark matter. But at small scales, free electron fluctuations are strongly damped due to stellar and AGN feedbacks. So in the bottom panel, the bias factor is unity at largest scales, but at small scale, it is damped, strongly damped. And our analytical model uses these fitting functions, this fitting curve and previous this fitting curve for free electron abundance and power spectrum. We also made mock sky maps of DM based on a standard ray tracing technique. And here it's an observer, and we placed simulation boxes along line of sight, and field of view is 6 by 6 degrees squared. And we calculated free electron column density along the straight ray path. And this is an example of the contour map at source redshift 1, but I skipped this one. And this figure shows the mean and the 1 sigma scatter of dispersion measure. And the vertical axis is DM divided by source redshift, and x-axis is the source redshift. And these colored symbols are simulation results, mean with 1 sigma standard deviation. And solid and dashed curves are based on a prediction of our analytical model. Mean and plus minus 1 sigma deviation. And you can see our analytical model agrees well with the simulation results. And this figure is the probability distribution of DM for source redshift unity, but I skipped this one. And this figure is probability distribution of source redshift for a given DM dispersion measure. The probability distribution as a function of source redshift. And here, the dispersion measure is fixed by 1000. And the colored histogram are the simulation results. And it's how can I say, the scatter in source redshift is about 20%. And you can see the simulation results are well fitted by a Gaussian distribution denoted by the red curve. Finally, we also compute angular 2-point correlation function of dispersion measure. It's a correlation function between the dispersion measures at different sky positions at theta 1 and theta 2. And here, the theta is angular separation between them. And then the angular cross correlation is defined by this equation. It is a standard definition, I think. And our analytical model predicts this correlation can be described by the simple expression. The cross correlation is simply proportional to the inverse of theta for large angular scales larger than 1 degree, and source redshift is larger than 0.3. And we expect this correlation function will be detected using thousands of FRBs in the near future. And this figure plots angular cross correlation function for ideal full sky observation measurement. Angular cross correlation as a function of angular separation theta. And in the vertical axis is correlation function times angular separation theta. And the red curve is our analytical prediction. And shade regions are 1 sigma error regions determined by survey area and shot noise here. And in this plot, we assume host galaxy, the dispersion measure scatter by host galaxies are 50.
About 3 minutes, Ryuichi.
Okay, thanks. And orange dashed line is our simple power of it, and this one. And these different shaded regions correspond to different number density of host galaxies. For example, the lightest shaded region corresponds to 0.1 host galaxies per degree squared, and the darkest shaded region corresponds to 10 host galaxies per degree squared. And these error bars are at large scales. The error regions are mainly determined by the cosmic variance. And we also make our numerical code publicly available. And our numerical code computes free electron statistics, for example, abundance and power spectrum, and also DM statistics, mean, variance, angular power spectrum, and angular cross correlation function based on TNG simulations. So if you are interested in our code, please visit our archive page and click here. This is our conclusion. Yes, that's all. Thank you.
I see that Caitlin Shin raised her hand. Maybe she's not here anymore. That's fine. Are there questions to the speaker? I don't think the speaker is here. He's in Japan. If there are no questions, I guess we should move on to our next speaker. The next talk will be a live talk given by Dana Simard. She's from Caltech. She will talk about turbulence in extragalactic ISM illuminated by FRBs. Go ahead.
All right, thanks, London. Yeah, so I'm Dana Simard and I'm a postdoc at Caltech. And today I'm going to talk about ways to use fast radio bursts to understand the properties of the interstellar media of their host galaxies. And this is recent work by myself and Vikram Ravi, which you can find on the archive at this archive number. So I'll start by talking a little bit about turbulence in the Milky Way and what we know and how we know it about the Milky Way. So within our own galaxy, we have the benefit of many different tracers of both velocity and density fluctuations that have been used to build up this picture of turbulence in our own galaxy. And we have this information over this remarkable range of scales. So at scales of about 10 to the 18 meters, we're looking at velocity fluctuations in the interstellar medium. And then on the other end of the spectrum, at about 10 to the 7 meters, we have access to information from scattering of pulsars and also of extragalactic sources. And by amalgamating all of these tracers, it's found that the turbulent power spectrum in the ISM of the Milky Way very closely follows the spectrum that Stella put up in her talk earlier, where the density fluctuations are parameterized by a simple power law between the outer scale at which energy is injected into the turbulent cascade and the inner scale at which energy is dissipated from the cascade. So in addition to the index of this power law spectrum, to characterize turbulence, we also need the fluctuation amplitude, which here I've called Cn squared for the density fluctuation amplitude. Even though we have all of these different tracers in the Milky Way, and even though we've been able to build this remarkable picture, some questions still remain, especially at small scales, where the existence of extreme scattering events suggests that maybe we're using some tracers to understand these small scales that actually are not tracing the same turbulent spectrum. Oops. When we move to looking at other galaxies and trying to understand turbulence in other galaxies and how things like the support to, contributed by turbulence to these galaxies might be different than our own Milky Way, we lose access to a lot of these tracers that we have in the Milky Way. So at the large scale end of the spectrum, we still have access to velocity fluctuations, even in cases where we may not be able to make a velocity map of these galaxies. And this is through the non-thermal widths of lines, of emission lines in these galaxies. And so it requires us to be able to compensate for both the possibility of bulk motions that are contributing to these widths, as well as thermal motions. So we need some modeling of those contributions to the widths of these lines. But if we can account for those, then we can use the line widths to measure the velocity fluctuations at the outer scale, so at about 10 to the 18 meters. Unfortunately, pulsars are not luminous enough to be seen in galaxies like FRB host galaxies, but fast radio bursts undergo scattering like pulsars, as we've heard previously in this session, and are affected by density fluctuations in their local ISM. And in this case, this is sensitive to fluctuations below the Fresnel scale, and so we're probing the very small scale range of the spectrum at about 10 to the 8 meters. And so my goal with this talk is to show you that we can combine these two tracers in order to learn something about turbulence in the ISM of these host galaxies. And so in order to combine these tracers, we need to know both this power law that relates these tracers on, or we need to assume something for this power law that relates these tracers over 10 to the 10 or over 10 orders of magnitude. So we can assume things, we can assume that it's similar to the Milky Way. We have a similar power law index beta and similar inner and outer scales. But we also need to relate the amplitudes of the velocity and the density fluctuations. And this depends on some properties of the gas, including the sound speed and the electron density. So we need to assume something or know something about these parameters as well. And so today I'm going to talk about a specific type of case study that we included in this paper, where we looked at FRBs that are near or coincident with H-alpha regions in their host galaxies. And these are nice examples because we can probe the local turbulence to these FRBs by looking at the H-alpha or H-beta emission from these regions. And so this provides our tracer at about 10 to the 18 meters. And also because we know something about the temperature of the gas that we expect to be emitting at H-alpha. And so we can also model the thermal contribution. And then at small scales, we're looking at the scattering timescales of fast radio bursts, or limits on the scattering timescales. And we're going to try to compare that to what we see from the velocity dispersion in the H-alpha regions. So we can make these assumptions to try to compare these 2 points. We only have 2 points on the spectrum. And if we see an inconsistency between these 2 points that we have, it means one of our assumptions is wrong. So for example, it could mean that something is contributing to scattering of the fast radio bursts, but not to the width that we see from the H-alpha region emission lines. And so this could happen if there's some smaller structure that is contributing to scattering of the fast radio bursts. Or it could mean that we have something wrong about this power law spectrum. So for example, that the index that we have is not correct, or the index that we've assumed. And so in this way, we're able to probe the properties of turbulence in the extragalactic ISM. But also, if we can distinguish between these two cases, we can say something about the local environment of the fast radio burst, and if it is in an environment that has special scattering compared to the rest of the interstellar medium of its galaxy. So today, I only have time to really focus on one of the case studies that we presented in our paper. And the one I'm going to talk about is 2019-0608b. And so we've already heard a little bit about this source in this conference. This was a source that was discovered and localized by ASCAP and is found to be coincident. The localization region is coincident with this knot of star formation in the spiral arm of its host galaxy. And it's also a source that has a measured extragalactic scattering delay of about 3.3 milliseconds at 1.3 gigahertz. So Sunil Simha led this very detailed investigation of the dispersion measure and scattering distributions for the source, which included modeling the foreground galaxies in order to determine how the IGM might contribute to scattering, and found that it's very unlikely that there is a foreground galaxy or foreground structure that is contributing to scattering. So as this time scale is inconsistent with what we expect from the Milky Way along this line of sight, it's very likely that this scattering is actually arising in the host galaxy, although we can't say that for sure. And so using this analysis, I've calculated the power in turbulence from these two tracers. So from, in this case, the H beta velocity dispersion and the scattering measure, or the scattering time scale of the fast radio burst. And so these are shown on this figure in the middle here as the blue circles. And so you can see quite clearly that if you extrapolate from the blue circle at about 10 to the 18 meters, or 10 to the minus 18 for the spatial wave number on the left-hand side of this plot, down along the dashed line here, which is our assumed value for the power loss slope of about 11/3, that the result that we would infer or predict for the FRB scattering is 5 orders of magnitude lower than what we actually observe from the scattering timescale. And so we're seeing that there's a much greater power in the turbulence in the small scale fluctuations than what we would expect from the large scale fluctuations for this source. So we can now use this to try to say something about the ISM, or the host galaxy, or the local environment of the fast radio burst. And so one thing we could do is vary this power law index beta, and we require something of about 3.2 for this index instead of 3.7, which is what our Kolmogorov scaling, or 11/3, that is consistent with the Milky Way ISM. But this could also be due to a bump in the power spectrum at small scales. And this same conundrum, where you have this increase in power in small scales, is seen towards the galactic center. And in order to differentiate between these two possible cases, we really need additional tracers. So we could imagine using intermediate tracers of to constrain the power and the fluctuations at intermediate scales. So in the Milky Way, we use DM variations and fringe tilt in the dynamic spectra of pulsars to constrain these intermediate scales. Both of these are things that we can consider doing for fast radio bursts if we have enough bursts, repeat bursts within a very short period of time, in order to really probe these variations. But they are only applicable to repeaters. And so we're limiting ourselves to repeat sources and highly active repeating sources. On large scales, we can look at modeling resolved emission lines. This is something that has been done in the Milky Way with neutral gas, but hasn't been tried with ionized gas or outside of the Milky Way. But another option is to look at constraining the slope on small scales. And this is something that has actually been done for this source. And we do this by looking at how the scattering evolves with frequency. And Cherie Day looked at the scattering properties of this source and found a value for beta that we would infer for isotropic scattering that is consistent with either of our cases. So either a Kolmogorov turbulent index or something shallower. And so there's still some uncertainty here as to what is really causing this increased power on small scales. I hope I have convinced you that this is a promising way to look at small scale. Perfect, thanks, Wenbin. to look at small scale turbulence in the ISM of FRB host galaxies, which can tell us both about the host galaxy ISM as well as about the fast radio burst source environment. I didn't get into it today, but using the Milky Way, we can, in some cases, actually constrain the location of scattering. I think this has been talked about quite a bit in this conference of using the fact that we see scintillation in scattering tails of fast radio bursts to tell us that the scattered disk of the fast radio burst is unresolved to the scattering screen in the Milky Way. And to do this, what really matters most is having a large bandwidth, so that even at even in cases where we expect a very large scintillation bandwidth in the Milky Way, we would still be able to resolve that for our sources. And so future FRB surveys will be quite promising for doing this kind of work and actually attributing scattering to fast radio, to the local environment of fast radio bursts. And then in order to improve our accuracy of our comparisons of these two tracers, we can really rely on we can really benefit from having improved constraints on the properties of the gas. So things like improved emission measure constraints and H alpha surface density flux constraints by looking at really resolving the emission regions, as well as looking at different emission lines in order to model the thermal motions of the gas. So these are things that I think will be quite promising for future studies. And additional tracers, especially getting intermediate constraints for repeat bursts or looking at scattering evolution with frequency, will also help us to distinguish between these two different cases that we found for the case study that I presented today. So thank you.
Thanks for the talk. So we have a question from Javier Prochaska. Just checking, how was the velocity dispersion of the H2 regions estimated? Whether were rotation, spectral resolution accounted for?
Yeah, so in this one that I presented today, so this is here I'll go back. Yeah, so this case study, it was an H beta map with KCWI, and we used the velocity dispersion within the map. But for the other two case studies that we look at in this paper, which are 1809-16 and 1211-02, we do use the widths of the emission lines. And in both of these cases, those widths may be unresolved. And so these may be upper limits, and having high resolution spectroscopy to resolve those emission lines would be very interesting, I think, for improving these constraints.
So I have a question on this plot on the right. I want looking at the one with the larger wave number, meaning smaller scales. How is the horizontal axis, the position of the horizontal axis determined? Maybe I missed.
Yeah. So in this case, we're using the Fresnel scale so any fluctuations that are smaller than the Fresnel scale will contribute to these, but it'll be dominated by fluctuations at the Fresnel scale just because of the index of the spectrum. So we've made some assumptions about where this screen is in order to calculate the Fresnel scale. And we're assuming that it's about 150 parsecs away from the source.
Oh, I see.
So basically,
like 1 parsec away, would it affect much?
Yeah. So if it is, I believe the Fresnel scale is proportional to the square root of that separation. So it is, it would change this. Yeah.
Mm-hmm. Thanks. Are there other questions from the audience? Okay, it looks like there are no more questions. Thanks, Dana. We will move on to our next talk, which will be a recorded talk from Amanda Cook from University of Toronto. And she will be talking about constraining the plasma in the Milky Way's halo with CHIME FRB.
My name is Amanda Cook, and I am a PhD candidate at the University of Toronto. I'm supervised by Brian Gainsler, Gwen Eady, and Paul Schultz, and I'm a proud member of CHIME FRB. So I'm happy to share today what we've learned about the Milky Way's plasma using our FRB sample. So we've talked a lot about DM contributions already in this session, so I'll try to keep this brief, but as a radio signal travels through ionized media, it picks up a dispersive delay that is proportional to its inverse frequency squared. And we can measure this, and luckily it's also proportional to the amount of free electrons along the path as a column a path integral, column density. And so we can use this to study the properties of the free electrons. And so the DM that we measure for extragalactic bursts is a combination of how I define it for contributions. Starting at the source of the fast radio burst, it will first encounter its own DM host. This could include a disk, this could include a halo, this could include some kind of local supernova remnant, other contribution. Leaving its host galaxy, it will then travel through the intergalactic media, and this could include intervening halos, intervening galaxies. And then finally, it will reach our Milky Way and have to go through our halo and disk. And so the DM halo is an interesting contribution because the halo gas itself is too diffuse to be imaged directly. There are observables that we can use that we believe trace the gas content, like absorption lines in UV and X-ray. However, in order to get the total gas content from these observables, you need to make some model-dependent assumptions. And once you convert these various models into DM halo estimates, as done by Keating and Penn in 2020, they can span in an order of magnitude. And so this is interesting because if we had a really good measurement of DM halo, it could potentially inform galactic formation theory, because you might expect different contributions depending on how we made our halo in the first place. But I think another really interesting part of this estimate, which many of you are likely interested in, is any meaningful distance estimate that we make using fast radio burst DMs must have these foreground contributions subtracted. So we need a really precise DM halo estimate in order to do source or host galaxy associations if we don't have VLBI precision localization, as well as cosmological experiments, which we heard a lot about recently. So the premise of my project is super simple. If every fast radio burst is extragalactic, then in a given line of sight, every fast radio burst needs to pass through the halo and the disk, and hence every fast radio burst is an upper limit on the Milky Way contribution. This is to varying degrees, of course. Some will be very bad upper limits that are not very constraining, and some might happen to be on the outside of a very nearby galaxy, right in the globular cluster, and really constraining. So we have upper limits from the total contribution from the Milky Way, and then we can get lower limits on the disk contribution of the DM from galactic pulsars. So we can measure pulsar DMs. We expect pulsars to be mostly in the disk because of the massive stars from which they are born, they have very short lifespans, and also pulsars which are very far away are pretty dim, and so we don't really expect to see them. And so if we subtract this upper limit the lower limit from the upper limit, we get an upper limit on DM halo, and it's purely observation based. And so that is what we're going for. And so let's kind of flip this picture on its side and look at the data that we have. So here are our FRBs in pulsar sample. This is DM versus sign of galactic latitude, but the absolute magnitude is taken. On the top, we have in triangles fast radio bursts detected by CHIME FRB, where I've noted which ones are repeaters and which ones are as of yet non-repeating. And then on the bottom in the stars, we have galactic sources like pulsars from the ATNF catalog. Those are shown in gray. And then all of the detected galactic sources with CHIME FRB are shown in this darker color, just to kind of show that we have some sensitivity down here. But what's really striking is that there's a pretty clear gap in what we're seeing between extragalactic fast radio bursts and and our galactic sample. And I am here to claim that this is at least partly due to the halo, and let's build up on this plot a little bit more. So I think the first thing that I should share is the Milky Way disk model. So I've plotted 3 models here. The first 2, YMW16 and NE2001, aren't really a disk model. They're actually free electron density models of the entire galaxy, but we can use them to predict the maximum DM as a line of sight, and notably neither of them contain a component in their model for the halo, so it might be appropriately used. But I think most relevant is that CHIME FRB uses these models to determine which FRB candidates we save intensity data for. So they should definitely be considered. And so the spans in the YMW16 and NE2001 show this collapse over longitude. So it shows the range over each longitude, but only for lines of sight with declination greater than -10, which is where CHIME FRB is seeing, and only for lines of sight without really high emission measure, so that we don't probe local structure like H2 regions and other things that we're not super interested in. The last legitimate disk model is the Ocker et al. 2020. So the authors in this paper went about describing the scale height of the thick disk using pulsars with independent distance derivations. And so if you take the scale height, you can convert it into a estimate of the disk contribution to the DMs in any given line of sight, if you assume just a slab geometry of the thick disk. And so that is the yellow span, where here it's actually the model errors that this takes up the span. And so you can see we have some fast radio bursts that are really great probes, really low DM, but it's limited number of sites. So we want sight lines. And so we wanted to make a kind of a smooth argument between these to say, what could we reasonably conclude between our best lines of sight? And so one of the models that we use is just a simple cubic polynomial. However, it's a cubic boundary estimate in that we enforce 2 things. The first thing is that all of the FRB DMs must lie above this boundary curve for the galactic DM. And then the area between this curve and DM equals 0 needs to be maximized. That is, we're taking only the most conservative estimate we can that still supports this data. But obviously this is super dependent on the model that you're putting in. So another one that maybe could even, I would argue that there's a little bit too much structure in here that to be physically motivated by the FRBs we have, but just it might be more conservative depending on your use, is the low S boundary estimate. So low S stands for locally weighted scattered plot smoothing. It's basically just a fitting method which penalizes outliers. And instead of using fast radio or the DMs directly to fit, because our outliers are actually our best points, we define the data at every sign B as the local minimum in 5-degree bins. Finally, or not really finally, but a lot of the halo models that I'll talk about assume some kind of spherical symmetry of DM halo. And so we can do this type of model using our most constraining fast radio burst, FRB2021 aka the repeater in M81, which I'll probably refer to it as because I think it rolls off the tongue a little nicer. So if you assume, again, this Ocker et al. 2020 slab geometry for DM disk, you can find the maximum total amount that you could attribute to the halo for this M81 repeater. It's 52 DM units approximately, and then we just plot this above the Ocker et al. Disk contribution as a function of latitude. And then mostly just to guide the eye, I have a constant, but I don't have to explain that one at the M81 repeater. And so the results are essentially, depending on which model you choose and which galactic latitude you're looking at, data-based constraints for the Milky Way contribution to the DM that range from 80 to 151 DM units, and then halo constraints that lie between 45 and 119 DM units, again, assuming a certain model in galactic latitude. And so if you're looking at this gap and thinking, okay, that's tantalizing, but there could be other things at play here, I'm not sure if it has to be the halo, we're all with you. And I should talk a little bit about what else is likely contributing to this gap. So we've proven pretty certainly that at least the excess DM is a proxy for distance. And so when we're searching lower and lower DMs, we're also searching less and less volume. So you could imagine that we're not detecting fast radio bursts down in the gap just because of the smaller volume probed. Similarly, due to CHIME FRB's RFI mitigation strategies, we are slightly less sensitive at low DMs. And so I just did a really simple experiment estimating the ratio of the number of sources within these two volumes, accounting for CHIME FRB's selection function. And I find that it's inconsistent. Our observations are inconsistent with the volume and instrument bias alone at a very conservative greater than 3 sigma. My argument was like very simply conservative, and I can come back and talk about it if people are curious, but definitely above 3 sigma. And at the 90% confidence level, you need more than 20 DM units from the halo or host to explain the observations that we're seeing. And so, wow, that's a lot of text. Don't worry, I'm not going to drag us all through that. I could not possibly do justice to all of the models that I will compare to today in the time I have, but I just wanted to give a proper legend in case people are on YouTube and want to pause and look at this. But I will say that the majority of the data that I have here, as well as the notation that I follow, is taking from Prochaska and Zhang and Keating and Penn, which are great reference papers, and I would totally recommend the read. But I just kind of wanted to give a feel for how good these constraints are, or what the power they have is to differentiate between models. And so I'll kind of point out the highlights. We have known for a while, and this continues to confirm that the NFW profile is inconsistent. That is, we don't expect the halo gas to trace the dark matter. Most of the spans in this plot, in the lower plot of predicted DM halo, represent different input parameters, mostly high and low mass halos. And it seems like most of the higher mass scenarios of the halos in these models are ruled out. They seem pretty inconsistent with our observations. I see a lot of time people citing, when they're trying to estimate a halo contribution, they cite Dulag et al. 2015, and they say 30 will attribute 30 to the halo. And I think that cosmological simulation remains quite relevant, looking at their spans as well. Finally, the Miller and Bregman 2013 paper is low, but you could still explain it away if the Milky Way halo is very clumpy, or if the DM from the M81 halo is much, much larger than the DM from our own Milky Way halo. I also have kind of a special plot for Yamasaki and Totani 2020, because they give estimates of the predicted DM halo as a function of galactic latitude and longitude, as they don't have spherical symmetry. So you can see how our galactic latitude models compare to theirs, and I think it agrees pretty well. There's some overlap, which could be concerning. However, since this should be a very strict upper limit, a very conservative upper limit, but again, they have to integrate over longitude, which we don't. And so at the M81 repeater spot, they're only predicting a DM halo of just over 30 as well. So it does seem roughly consistent. And the Yamasaki and Totani 2020 also helps me talk a little bit about the model uncertainties that we're facing here. So I haven't had any error bars on here yet, and it's because it's a little bit of a complicated picture. So obviously we should examine how legitimate it is to collapse over galactic longitude. If you look, so they looked at the scatter and the X-ray emission measure data, and they find that it implies for the Milky Way halo DM a fluctuation of 0.2 dex over the whole sky. And so that's what this looks like on our model. Obviously, for any fit that you run, there's some fit errors. So we can do a bootstrap to find a 90% confidence interval point-wise for this fit. And I think the one that's like the most glaring is that to this point, I've been very careful about not making any assumptions about what the host or the IGM contribution might be. But these things, especially for the most nearby repeaters, are often very well established, and you can make just a basic assumption about things being Milky Way-like and using the Makar relation to give an estimate of the isolated DM halo. So Mohit has a really great paper describing exactly what you expect this estimate to be in his M81 repeater discovery paper. But this is kind of where you might expect, how much lower you might expect it to be just in that one case. And so the true answer is likely a combination of all of these effects. And this part is a little bit of a work in progress. We're hoping to have this completed quite soon to share with the community. And so I guess that brings me to my conclusions. I'm maybe a little bit fast, but we present FRB derived constraints as a function of galactic latitude for the plasma in the galaxy and the Milky Way halo. These observation-based high latitude constraints for the Milky Way as a function of galactic latitude are between 80 and 151 parsecs per cubic centimeter, depending on which model you're choosing, whatever makes the most sense for your given case. And then subtracting the Ocker et al. Estimate for the DM disk, we can get DM halo isolated between less than 45 and 119 DM units. The future work is, well, we're trying to complete this paper right away, including the curve formulae and the full interpretation very soon, and you can see all of the models in their full glory. But then also, I guess, longer down the road, we're going to do a comparison of the longitudinal behavior and a 2D map. I kind of expect this in about 2 years at our current detection rate. We'll be able to make a distributional argument, as well as a good majority of the sky will be pretty well resolved. But I think that there's lots of potential surprises given by the universe. So we'll see what it gives us. If we have a lot more M81 repeaters, I think that this could come sooner, or if we suddenly have a better idea of a large fraction of the fast radio bursts coming from a particular host, then maybe that would help us. Yeah, so thank you for the organizers for letting me speak, and I'm happy to take any questions.
So we have a question from Nicholas Tejos. Anyway, Amanda is not here, but we can still discuss. The idea here is that the DM gap is mainly from the DM contributions of the Milky Way halo or Milky Way halo plus local group. I guess it is from the Milky Way halo. Okay, Brian, yeah, can we promote Brian Gensler into?
Hi, so the question, can you just repeat the question? I'm not seeing it on the
yeah, the
chat.
question is, the idea here is the DM gap. Is it mainly because of the DM contribution of the Milky Way halo or halo plus local group?
So at the moment, we are assuming that it's all due to the Milky Way halo. In order to be able to disentangle the halo from the local group, you'd have to look for a sky dependence of the gap. And that's something that we don't think we can do much with our current data set. But as Amanda says, on the last couple of bullets, in about a couple of years towards the end of her thesis, we'll have enough FRBs that we can look for a positional dependence, and then we can actually start to decompose, a quasi-spherical halo from sort of the more ellipsoidal distribution you'd expect around the local group. So at the moment, they're sort of degenerate. Okay,
Sturrow has a question. Can you comment on the use of Milky Way globular cluster pulsars? He was mentioning M53 has 4 pulsars with DM25 at 18 kiloparsecs and B of 79 degrees, almost straight up, similar to other clusters.
Yeah, so the DM contribution from the clusters aren't that high up in the halo. And if you plot the vertical component of the DM for all of the known pulsars and globular clusters, there's basically no measurable increase in DM as a function of scale height. So the globular clusters aren't very constraining, essentially, because they're just probing the inner part of the halo, and most of the DM contribution here is farther out than where the globular clusters are.
So I have one more question. So looking at where Amanda showing the DM gap, it looks like there is some the number distribution in DM, right? So in the CHIME let's say if CHIME selection is, let's say, uniform in DM, roughly uniform in DM, the DM distribution should tell us, right, there should be accumulation of DM near the DM halo, right? Does that tell us something about the DM halo at this point?
So you got these two competing effects. One is that there's this lower limit, but also the volume of the universe is decreasing. And when you combine, and so there should be few, and that causes fewer FRBs. So when you combine those, you don't see that pile up. We originally thought that we would see that pile up, but when you simulate this, the decreasing volume means you just don't see it, at least not with the current sample.
I see. It's the sample is just too small.
Yeah.
Are there any other questions? Okay, I think we should move on. So we have our last talk, which will be, it's a live talk given by Sunil Simha from University of Santa Cruz, University of California, Santa Cruz. And he will be talking about estimating the contribution of foreground halos to FRB 180924 DM. Go ahead, Sunil.
Thank you, Wenbin. Can everyone see my slides?
Yes.
Okay. All right. Let's begin. So, hi everyone. I am Sunil Simha. I am a graduate student at the University of California, Santa Cruz, and I'm working with Professor Xavier Pacheska, and more broadly with the F to the 4 teams and the craft teams. And today I'm excited to share some of our latest results on estimating the foreground contribution from halos to the dispersion measure of FRB 180924. So without further ado, let's begin. Now this has been mentioned multiple times before, but I'd like to re-emphasize on how the amazing ability of FRBs to shed light on ionized matter, basically resolving the missing baryon problem, which was an observational lack of a large chunk of baryons in the low Z universe. So this famous result by McCart et al. 2020 shows that there is indeed matter as expected from the lambda CDM cosmology, and because the expected dispersion measure as a function of redshift is followed closely by the observed FRB data points. So this shows that FRBs can clearly be used as cosmological probes, and they can quite literally shed light on the ionized gas in our universe. And so when I first started working here at Santa Cruz, the time was ripe for studying an FRB sightline, and we got really lucky with FRB 190608. This particular sightline happened, so this FRB was localized to this very beautiful spiral galaxy in the SDSS footprint. It is located at a redshift of 0.1117. So it's fairly close by. And because it's in the SDSS footprint, we also have large-scale spectroscopic coverage. That is, we have redshifts of a whole bunch of foreground galaxies, or field galaxies. And so as part of our work, so two papers, one led by Jai Chitri on the host galaxy and its halo, and the other one led by me on the foreground universe, we were able to perform a very detailed analysis of the sightline, starting with, of course, the Milky Way contribution of the dispersion measure. We're using the NE2001 model, and a halo contribution, assuming a halo gas distribution. Same thing for the host galaxy too. Jai Chitri led a very detailed analysis of the light from the ISM, the host ISM, and we were able to lay constraints on the dispersion measure. The work that I led concentrated on the foreground structures. More specifically, we were able to constrain the amount of dispersion measure that came from the intervening halos, the gas that is virialized within foreground halos. And also we were able to make a detailed reconstruction of the diffused gas in the IGM. And we were able to estimate the dispersion measure contribution independently. And so in summary, we were able to show that roughly 33% of the dispersion measure comes from the host and halo, About a quarter comes from the Milky Way and its halo, roughly 5 to 8% from the virialized gas within foreground halos, and the rest of it comes from the diffuse IDM. So this was a proof of concept. It showed that we were able to independently estimate the dispersion measure using purely optical observations, and we were able to tally it with the radio observation. And in this particular case, we showed that the two were in agreement with each other. But of course, this analysis unlocked interesting possibilities. KG Lee had already mentioned in his talk in session 10 that we now have plans to perform this sort of analysis for multiple FRB fields. And we want to start laying constraints on the fraction of the universe's baryons that lie in the diffuse IgM, for instance. And also, even with individual sightlines, let's say there's one in the future where we find a significant excess DM after doing this analysis, that would imply the existence of some sort of electron reservoir, like the electrons in a galaxy group, for instance, or some such foreground structure, or maybe even the progenitor environment, for instance. So a lot of interesting work can be done with this sort of analysis. So having analyzed this sightline, it was time to move on to the next one. And this time I chose FRB2021 It was the first non-repeating FRB localized by ASCAP to a host galaxy. And this sightline was interesting for a number of reasons. The first one being that if you look at the location of this FRB sightline in the McCart plot, you see that it is lying below the mean McCart relation, or the McCart relation as it's called. So this implies that there could be this particular sightline could be underdense, either in terms of halos or the filamentary structures. So this was a hypothesis that we certainly wanted to test. And another reason why this sightline was interesting to us was basically a technical hurdle. Namely, we did not have extensive spectroscopic coverage for this field like we did for 1906-08. At the time we started this work, we only had a MUSE IFU observation of basically a 1 arc-minute field of view around the FRB. So this is what the observation looks like. So what we have on the left over here is a white light image. So if you take the data cube and you squish it along the wavelength axis, this is the image that you get. So you can see the FRB, its host. Well, you can't see the FRB in the image, but you can see the host. And we also get spectra of all of these, well, most of these objects. And we are able to estimate their redshifts directly in one go. So we were able to determine a lot of these sources were background sources like these ones over here. But also more importantly, we were able to show that there are 2 foreground sources whose spectra are shown over here. So these foreground sources were both roughly 100 kiloparsecs away from the FRB sightline at their redshifts. So this is all interesting, but this is not enough information. And so my idea was to try to use photometric redshifts to lay at least some constraints on the dispersion measure contributions in the foreground. Specifically, because this particular sightline was there in the DES DR1 footprint, and it also had WISE coverage. So we basically had photometry in the UGRIZ and the W1 to 4 bands. And so the idea is fairly simple. We want to get a PDF for the the photometric redshift, or the redshift based on the photometry. And we want to convert that PDF to a PDF of the dispersion measure contribution of that particular galaxy. So this is the basic picture we have. So there's the FRB, there's the halo, it's intersecting at some point. We want to measure how much DM it contributes. And we want to do this for all the galaxies in the foreground, and by doing so, we can then start laying constraints on the total dispersion measure from the foreground halos. And so this is the methodology that we came up with. I will try to explain this very briefly, and of course you can go back to my paper, which will be soon on arXiv, and look at it in more detail. But essentially, we start with a PhotoZ PDF that we estimate using a software called EASY. And using the realizations of those redshifts, we are able to produce realizations of stellar mass, again, using SED fitting with another software called SIGAL. We are able to convert the stellar mass values to halo mass values using the stellar to halo mass ratio relation, using the one from Moster et al. 2013. And using, now that we have a PDF of halo mass values, we can then produce a PDF of dispersion measure estimates for each individual galaxy. And combining all of these galaxies, we get the final PDF of the dispersion measure. And so this is what our results look like. So here's the limited, the field of view of the Muse data cube. So as you can see, it's just a very tiny amount, but we have large scale imaging data. So this is the this is the R-band image from DES. And you can see, so we have expectation values for the dispersion measured from each of these foreground galaxies. So the squares over here are colored and also appropriately sized to show this expectation value for their dispersion measure. And this is what the total, the PDF of the dispersion measure contribution in total from halos using just photometry looks like. So we have a mean value expectation of roughly 13 parsecs per centimeter cube. Of course, we also got the spectroscopic galaxies, so the galaxies with spectroscopic redshifts. So combining that sample, which is fairly small, basically 2 plus another one from LRIS, and this photometric sample, we can say the mean contribution from halos to the FRB dispersion measure is roughly 21.4 parsecs per centimeter cube. And so this figure over here shows 3 minutes.
Yeah.
Thanks, Wenbin. Thank you. Right, so this plot over here shows dispersion, the cosmic dispersion measure, that is the DM estimated after subtracting, so there are 3 ways you can measure this or estimate this. One, you can just subtract the Milky Way and the host contributions from the FRB. That's what this red point is. You can then use the McCart relation and look at its scatter. So this is the dotted line over here is the McCart relation. And as you can see, it is below the mean. And also using our own analysis and with a little bit of cheating for the IGM, or the diffuse IGM contribution of the dispersion measure, we just assume that the sightline is average. It is not really so. We would require further analysis to do this, but this is a good 0th order estimate of the IGM, diffuse IGM contribution. So adding that to our dispersion measure from halos contribution, we see that it is. So this is the line that we get, this is the curve that we get, and it's fairly consistent with what is observed. And so this is all well and good. So this brings me to my penultimate slide. on results and conclusion. This figure is from a future, going to be part of a future work. So that's why I would request people to not post share this online. But essentially, we were able to, through this analysis, we were able to confirm that the FRB sightline of 180924, which is circled over here in this McCart relation, it's sort of enhanced plot, which shows the PDF of the scatter as well. So the PDF of the dispersion measure in the McCart relation as well. So you can see that this particular sightline lies close to the median value in our universe. So this is what we would typically expect for most FRB sightlines. And we were able to show that there's, since there is no foreground halo intersecting below or much less than 100 kiloparsecs, the dispersion measure contribution from halos in this sightline is fairly low. And so this is a typical sightline as it lies pretty close to median value. Going to the future work, as my last slide. So we have quite a few localized FRBs, and using a very rudimentary preliminary analysis, we are able to determine their cosmic dispersion measures. And it looks like they are, many of them are lying far above the McCart relation. Whereas we would expect from simulations, or even if you look at this scatter, the PDF coloring, you would expect a large number of sightlines to lie below, on the other hand, as opposed to above. And so a bunch of interesting things could be happening over here. Firstly, well, the most uninteresting solution, of course, would be that we have underestimated the host dispersion measure. It's probably not all that uninteresting. It could be a very cool project by itself. The most interesting to me is that some of these sightlines could be having interesting or foreground overdensities in the form of galaxy groups, or maybe some other sort of electron reservoir that we can try to study. This will also tie in with the flim-flam survey that K.G. Lee mentioned, and we will start laying constraints on the fraction of diffuse gas in filamentary structure and such. So with this, I come to the end of my talk. Thank you for your patience, and I'm happy to take any questions at this point.
Thanks for the talk. Are there questions to the speaker from the audience? So I guess, well, other people are still thinking. So you think these ones above the McCart relation, they have at least one halo that are kind of above normal, like 100 with the halo of 100 for these ones?
That is certainly an interesting possibility. Of course, I do not know at the moment. This is something that we're trying to find out. We have started collecting data, spectroscopic data of the field galaxies. It is possible, at least, if not, just a nearby galactic halo, it could be that there is a galaxy group or some such large-scale structure that could be heavily contributing to the dispersion measure, of course.
Yeah, how much resources do you need for each of the sources, each of the sightline?
Oh, that's a good
photometry?
We would search. So this analysis only requires multi-band photometry, but in order to do a full IGM reconstruction like we did for 1906-08, it would require, at least at the moment, good spectroscopic data. So let's say, roughly 85% of the foreground galaxies, if we're able to get spectra of them, that would be amazing. And that's what we're trying to do with the flim-flam survey.
Great. Good luck with that.
Thank you.
So there is a question from Sterafini. Isn't it a priori improbable that so many FRBs at Z less than 4 have dense halos clusters on line of sight? Or do you think there is a selection effect?
Yeah, so it's probably unlikely that it's a cluster or something along the line of sight. So again, I need to emphasize that these are very preliminary results. And in plotting this figure, I have essentially assumed that the host dispersion measure contribution is roughly 50 divided by 1 plus z, which is probably small for most of these sightlines. And so it is still too early to say what could be causing this sort of clustering above the McCart relation.
Either way is very interesting.
Yep, thank you.
Thanks. So it looks like we don't have any other questions. Let me check the Slack channel. Okay, so so that will be it for this session. Thanks so much for our speakers. Let's clap for them. And then after this, we will have our coffee break on Gather Town. Jason has already posted the link to the Gather Town. So we will see each other at the Gather Town over coffee break. Thanks so much for everyone to join us.